Human beings have always been fascinated by time. We measure it, we celebrate it, we fear it. But what if we could control it? What if we could travel through time, visiting the past or leaping into the future? Time travel has been a staple of science fiction for centuries. From H.G. Wells' The Time Machine to the iconic DeLorean in Back to the Future, the idea of time travel captures our imaginations. But is it just a fantasy, or could time travel actually be possible? The answer, like many things in science, is complicated. To understand time travel, we need to change how we think about time itself. We experience time as a constant, ticking away at the same rate for everyone. But what if I told you that time is not absolute, that it can be stretched and squeezed like a rubber band? Join me as we delve into the mind-bending world of time travel, exploring the science that makes it a tantalizing possibility. Imagine this: you have two identical clocks, perfectly synchronized. You leave one clock on Earth and take the other on a high-speed rocket ship into space. When you return, something strange happens. The clock you took with you shows a slightly different time than the clock that stayed on Earth. This is not science fiction, it's a real phenomenon called time dilation. Time dilation is one of the strangest predictions of Einstein's theory of relativity, and it has been experimentally verified many times. How can this be possible? How can time move at different rates? The answer lies in the nature of space and time itself. Einstein's theory of relativity revolutionized our understanding of space, time, and gravity. One of the key insights of relativity is that time is not absolute, but is relative to the observer's frame of reference. Imagine you are standing still on the ground and you see a train speeding past. From your perspective, time seems to be moving slower on the train. This is because the train and everything on it is moving very fast relative to you. The faster an object moves, the slower time passes for that object relative to a stationary observer. This effect is very small at everyday speeds, which is why we don't notice it. But at speeds approaching the speed of light, time dilation becomes much more significant. One of the most famous thought experiments in physics is the twin paradox. Imagine two identical twins. One twin stays on Earth, while the other twin embarks on a high-speed space journey at a significant fraction of the speed of light. According to Einstein's theory of relativity, time slows down for the twin traveling at high speed. So, when the traveling twin returns to Earth, they will be younger than their Earth-bound sibling. This paradox highlights the bizarre nature of time dilation. It seems counterintuitive that both twins wouldn't age at the same rate, but Einstein's theory shows that time is not absolute but is relative to the observer's motion. Section 5. Wormholes. Shortcuts through space and time. Wormholes are theoretical tunnels that could connect two distant points in space-time. Imagine folding a piece of paper in half so that 2 points on opposite ends touch. A wormhole would be like a shortcut through the fold, allowing you to travel between those 2 points much faster than traveling through normal space. While wormholes are still purely theoretical, they are allowed by Einstein's equations of general relativity. Some physicists believe that if we could create or manipulate wormholes, they could potentially act as time machines, allowing us to travel to the past or future. Section 6. NASA's timepieces, measuring the impossible. NASA has been at the forefront of research on time dilation. One of the most compelling pieces of evidence for time dilation comes from GPS satellites. These satellites orbit Earth at high speeds and rely on precise timekeeping to function correctly. However, due to time dilation, the clocks on GPS satellites run slightly slower than clocks on Earth. To compensate for this, engineers had to program the satellite's clocks to run slightly faster to ensure accurate positioning. This real-world example demonstrates that time dilation is not just a theoretical concept, but a measurable phenomenon that affects our everyday lives. Section 7. The future of time travel. Closer than we think? While we haven't quite cracked the code of time travel, our understanding of the universe is constantly evolving. As we delve deeper into the mysteries of quantum physics and explore the vastness of space, we may uncover new possibilities for manipulating time. Perhaps one day time travel will be as commonplace as air travel is today. Imagine hopping into a time machine to witness historical events firsthand, or to get a glimpse of what the future holds. Section 8. Ethical implications of time travel. The possibility of time travel also raises a plethora of ethical concerns. Imagine the potential for paradoxes if we could alter the past. What if we accidentally prevented our own existence or changed the course of history? These ethical dilemmas highlight the immense responsibility that would come with the ability to manipulate time. If time travel does become a reality, we must tread carefully and consider the potential consequences of our actions. Section 9. Conclusion: time travel, a dream within reach. The concept of time travel, once relegated to the realm of science fiction, is now a subject of serious scientific inquiry. While significant challenges remain, our understanding of the universe suggests that time travel may not be as far-fetched as we once thought. As we continue to push the boundaries of science and technology, the dream of time travel may one day become a reality, opening up a world of possibilities and challenges beyond our wildest imaginations.